Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and or questions, drop them in the comment section below or write to us, info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Right, so hello and happy new year to everyone. Let me welcome you to today's talk brought to you by the Oxygen Alliance. My name is Victor Nzembe, a biomedical engineer for the Oxygen Alliance, and I am your host today. I am hosting this call from Lilongwe, Malawi, and would like to know where you are joining us from, so you can type your name and location in the chat. For Oxygen Alliance communications, you can also type your emails in the chat so that you can be added on our emailing list. So in this year, for the first quarter of this year, we'll have a series on sterilization equipment. And the first talk will be an introduction to sterilization equipment. So this will just be an introductory talk, and more detailed webinars will follow under the theme sterilization equipment series. For this introductory talk, our presenters will be Preja Sambo, a biomedical engineer for the Oxygen Alliance, as well as Samuel Chingoka, who is a biomedical engineer under the Open Equipment Initiative. So at the end along the presentation, there will be a link of an attendance form, which will be pasted in the chat. So we request you to fill out the form. Just take note that as we did with the medical imaging equipment series, there will be certificates of attendance that will be issued to every individual who attend at least 60% of the webinars for this series. So without wasting much of your time, let me hand you over to our first presenter today, who is none other than Samuel Chingoka. Over to you, Sam.
Thank you, Victor. Hello, everyone, and good afternoon. As said, my name is Samuel Chingoka, and I am the biomedical engineer for the OpenO2. I'm proud this afternoon to be your presenter. So our topic is the introduction to sterilization equipment. Let's get started. So before we dive into the specifics of this topic, this is our presentation outline. We should look at it. We will start with an introduction to sterilization. Then we'll come to the types of sterilization equipment, which are heat sterilization equipment, radiation sterilization equipment, chemical sterilization equipment, and we'll look into the major parts of these types of sterilization equipment before we finish into sterilization cycles and phases. So let's get started. From just the word sterilization, just to say it even before we go into the definition, I hope most of us, we have an idea of what it is. So sterilization is indispensable when it comes to modern medicine and healthcare practices. So sterilization, this is a process where we want to destroy or want to remove, or I should say to eliminate all viable microorganisms, which are bacteria, viruses, fungi, or spores from a material or object, rendering it completely free of infectious agents. So when we say viable microorganisms, these are just microorganisms which they reproduce, they grow, and also they carry most of their cellular functions without a problem. So generally, these are infectious to humans, therefore want to eliminate them. So we are using sterilization. So sterilization plays a very critical role when it comes to ensure patient safety by preventing healthcare associated infections, which can lead to serious complications or prolonged hospital stays. Disinfection, on the other way, is a process that eliminates many or all pathogenic microorganisms except bacterial spores or inanimate objects. It is important that we understand sterilization in detail, and we also understand disinfection, because most of the people make a we don't really understand what this process does, because we can use disinfection instead of using in a situation where we are supposed to use sterilization. So in the disinfection process, we are eliminating some of the pathogenic microorganisms except bacterial spores. So both of them, there are ways that we want to reduce our microbial growth. Only for disinfection, we are not eliminating all, because there are some organisms, or there are some things, I should say, for example, the spores, which are just, they are like structures from bacteria which they have on themselves to protect themselves. So these spores, they are very resistant when it comes to heat or some chemicals. So that's what disinfection does. So after looking into the introduction, let us dive into our types of sterilization equipment. So, as in the outline, we have mainly three types of sterilization equipment, which are heat, chemical, and radiation sterilization equipment. So to start with heat sterilization equipment, we have two categories under heat sterilization equipment, that are dry heat sterilizer and also for the moist. So under the dry heat sterilizer equipment, this is where we use hot air that is at very higher temperatures. This is in the range of 160 to 180 degrees centigrade. Of course, temperatures may exceed this range depending on the type of pathogens that we want to eliminate, based on the standard that is used on tools and on tools. So basically that's the range. So with dry heat, we kill the organisms by oxidative damage. This is where we are using heat to cause oxidative stress. Just to explain it in simple terms, this heat disrupts the membrane of microorganisms, and it penetrates and kills these microorganisms. So under the dry heat, we have two ways in where we achieve this one. The first one, it's by flaming. So with flaming, we use a Bunsen flame, using a Bunsen burner to sterilize some of our products. For example, the inoculating wire. So next, we are going to see typical components of a Bunsen burner. So with a Bunsen burner, we have a flame where we are heating our object. In this case, it's a sterilizing inoculating loop. So by flaming, we are exposing it to very high temperatures, where we are going to kill these microorganisms. So basically, that's what flaming is. So apart from flaming, we achieve dry heat sterilization by using also a hot air oven. Basically, this uses electrically heated elements in a chamber. So in a chamber, it's where we have our objects we want to sterilize. So it is fitted with a fan for even distribution of air in the chamber. So we have some control systems. For example, we have a thermostat that is fitted to maintain the chamber air at chosen temperature and time that we have set. So this is a typical diagram to give us an idea of a hot air oven. We can see we have we have a door. Of course, it's not labeled. So we have the chamber, and we also have a vent that is we use after the process so that we can release the heat which is accumulated inside, so that after our objects they are cooled, we can be able to take out our objects. So under the heat sterilization equipment, as I said, we have heat sterilization equipment and we have those for steam. So on steam sterilizer, it's also known as an autoclave. An autoclave uses pressurized steam to eliminate microorganisms. So this is saturated steam, or it's also called the dry steam. That is, it is at equilibrium with water which is above the boiling temperature. So to be successful when we are sterilizing using steam, we need this pressurized steam which is saturated. We have key features for an autoclave, which includes temperature. And temperature, it's mostly in the range of 121 degrees centigrade to 134 degrees centigrade. We also have a very important feature, which is pressure. Typically, these pressures are of the range 15 to 30 psi. And we also have cycle time. So this is generally it's the time that it takes to sterilize our objects. So this is mostly in the range of 15 to 60 minutes. Let us come to the types of autoclaves. We have different types of autoclaves depending on how we can categorize them. But this one, it's based on how they function, I should say so. We have gravity displacement autoclave and we have a pre-vacuum autoclave. Under the gravity displacement, we use gravity to displace air with steam. So this is where we are putting steam into our sterilization chamber. By putting steam into our sterilizing chamber, the steam takes the space of air, because we understand that steam is denser than air. So air is vented out using a small orifice under the gravity displacement autoclave. And it's basically common for simple sterilization tasks. While under pre-vacuum or high vacuum autoclave, this is where we remove air before steam is introduced. Basically, we have a vacuum where we take out our air before putting steam into our system. So it is ideal for porous load. Porous load is just load that is wrapped. So when our load is wrapped, we want at all costs to remove every air which may also dwell in these wrapped objects, because air also has an impact that affects the penetration of steam to our objects we want to sterilize, whereby we cannot achieve our sterilization process successfully. So the diagram just shows the typical components of an autoclave, where we have the safety valves, we have the solenoid valves, we have the jacket pressure gauge, and you also have the internal pressure gauge, which is the chamber. We have a door, we also have a power control box, and we have sensors such as the temperature and temperature. So looking into each component in view, we have a chamber. This is where our items we want to sterilize, we put them into. We also have a door. The door has seals, which they have seals where completely we want to completely put a separate environment of where our objects want to sterilize to be. So these seals, they also make they make a tight sealing so that we separate our environment to the special environment where we want to sterilize our equipment, our objects. We also have a steam generator, as we have said that steam sterilizers, these autoclaves, they use the steam. We have a steam generator where we boil water to make it into steam so that we introduce it into our sterilizing chamber for the process. Part of removing air, we have a vacuum system. This just removes air from the chamber to ensure proper steam penetration. We have the exhaust valve and the vent. They just release the steam and air after the cycle so that we can make it safe when we want to open and get our objects. So about the safety valves and features, basically they prevent over pressurization, which include mechanisms like safety release valves. And so this is just another diagram uh, giving us an idea of this autoclave. So most of these parts I've already said, starting from the first diagram and also into the table that we had. All right, so continuing with the types of sterilization equipment, after heat sterilization equipment, we have radiation sterilization equipment. So radiation has two divisions. We have ionizing radiation and we have non-ionizing radiation. These are just categorized based on the type of energy that they produce. Generally, non-ionizing radiation has lower energies compared to ionizing radiation. So ionizing has this ability that it breaks the electrons from atoms or molecules. So basically, radiation sterilization equipment, it utilizes ionizing radiation to sterilize medical products. So we want to make it possible that we are able using the ionizing radiation to disrupt the DNA mechanism of our microorganisms and be able to kill them. Under the radiation sterilization equipment, as I've said that we utilize ionizing radiation, we have different types of ionizing radiation, such as the gamma rays, the electron beam, and the X-rays. But when it comes to sterilizing medical equipment, medical equipment, and some objects, basically, under the radiation sterilization equipment, we use the gamma radiation sterilizers and the electron beam sterilizers. So starting with gamma radiation sterilizers, we use gamma rays, typically from cobalt 60, which is our source, to sterilize these medical devices or pharmaceuticals. Under these radiation sterilization equipment, of course, they are used at small scale, but mostly they are used at a larger scale, such as in manufacturing industries, whether it's to do with pharmaceuticals or food and beverages. So under our typical components for these radiation, we'll see that we also have some parts which they are considering into a larger scale of this when this process is done. So under gamma radiation sterilizers, we have the radiation source. This is basically enclosed cobalt 60 sources which emit these gamma rays. We have the radiation chamber. It's just a protected area where products are exposed, so they are passed under this irradiation chamber so that they are sterilized. We also have a conveyor system that is on a larger scale, which transports products through the irradiation chamber to ensure that there's uniformity within the exposure. So we also have a shielding. They may be of thick concrete or lead walls, which protect the us and the environment from radiation exposure. We also have a control system, which we use it to monitor and regulate the radiation processes to ensure safety and effectiveness. So the diagram just shows us these typical components of a gamma radiation sterilizers as we have looked closely into them. So here we have the radiation source, mostly where we have the cobalt 60, which is our source. We have the radiation room, which is our chamber, where the products are passed, and we have this shield, which uh, protects the operators and the environment at large, because we know gamma rays, they are harmful to humans. We have these conveyor systems where our products are transported and they are offloaded. So this is a setup of a large setup, like the manufacturing setup. So we also have the electron beam sterilizer under radiation sterilization equipment. These are electron beam sterilizers. So they utilize high energy electron beam interacts with the products. So how does this high energy electron beam is created? So basically we have a source that is mostly a tungsten element, which is our source where we get these electrons. So the tungsten element is fed with a low voltage source, which after some time it releases these electrons. And these electrons, they pass through an accelerator that has field, high voltage field, where they are accelerated to high speed, which is close to the speed of light. So after this beam, we find this raster dipole. It's just an electromagnet which just bends this beam so that it creates this high energy electron spectrum, so that when our products are being passed, they are going to be sterilized. So the conveyor belt just gives us an idea of a large scale, like in a manufacturing setup. So the typical components of an electron beam radiation sterilizer, we have electron accelerator, as we have already looked into it, that it generates a high electron in this range of 3 to 10 micro electron volts. We have a beam transport system that directs and focuses the electron beam onto the target product. So like the gamma radiation sterilizer at a larger scale, we also have the shielding, the conveyor system, and the control systems. So what are the benefits and drawbacks of radiation sterilization equipment? Under the benefits, this process, this method for radiation, it's effective to sterilize already packaged products. So in a setup of like in manufacturing setup, it's an advantage, because after every process, they have packaged their products. They are just going to pass them under these high energies, the radiation, so that they are able to sterilize. And it does not require high temperatures. So at normal temperatures, when we say high temperatures, that is mostly they are not above 100 degrees. So they are good temperatures, mostly with the range of 45 to 65 degrees centigrade. Looking into the drawbacks, it is expensive to have this setup, and it can also destroy some material properties of biomedical polymers or plastics. So not every product or every material you want to sterilize, it's going to fit this radiation sterilization equipment. For example, some materials like the plastics, they are not ideal for this process, because they disrupt like the material composition. So it's not applicable for any material. So coming into our final chemical, our sterilization equipment, which is chemical sterilization equipment now. So chemical sterilization equipment works through the use of chemical agents to eliminate these microorganisms on surfaces and devices. So commonly used in healthcare, pharmaceutical, or biotechnology industries for equipment that cannot withstand high temperatures or moisture. So the common chemical sterilization equipment include ethylene oxide sterilizers and hydrogen peroxide sterilizers. So under ethylene oxide sterilizers, we use ethylene oxide gas to sterilize. So this one is effective for complex devices and materials that would be damaged under some sterilization methods such as steam or radiation. So that is our traditional ethylene oxide chamber where we have the tank and we have our load. And next is our picture that shows the real ethylene oxide sterilizer. So under the components, they are similar, that we have a sterilization chamber where we place our products that we want to sterilize. So we also have a vacuum pump where we remove air before we introduce the gas. We have a humidity control. This is where we just introduce water vapor because it acts as a medium for ethylene oxide penetration and microbial accessibility. So we also have temperature control where we have sensors that monitors our temperature. We have the ethylene oxide gas injector that after we vacuum or we take air out of our system, we feed the ethylene oxide gas into the chamber. We also have an exhaust, that is an exhaust fan and filtration system that safely vent out the residual gas. So this is just a diagram to show the typical components of an ethylene oxide sterilizer, where we have this vacuum pump, we have the chamber, we have the controls, and we have our gas tank. So lastly, under the chemical sterilization equipment, we have hydrogen peroxide gas plasma sterilizers. So basically, this uses vaporized hydrogen peroxide in gas plasma. So plasma is a commonly known the fourth state of matter, apart from the liquid, solid, and gas. So to a plasma state, it's where we have a partially ionized gas plasma. This is where we have a partially ionized gas that contains ions, electrons, or neutral atoms. So hydrogen peroxide ionization convert this hydrogen peroxide vapor into a reactive plasma state using energy such as lasers or high voltage electricity. So what this slide says is that under normal temperatures, hydrogen peroxide is in a liquid state. So it's usually heated to turn it into this vaporized state, and it is also it is ionized, or it is turned into a gas plasma form where it is called plasma, gas plasma. So next we want to look the typical components for this hydrogen peroxide gas plasma sterilizer before winding up. So the typical components of a hydrogen peroxide sterilizer, we have hydrogen peroxide reservoir, basically stores the liquid hydrogen peroxide, and we have a vaporizer that turns the liquid hydrogen peroxide into vapor that it is evenly distributed, and we have an ionizer that turns the vaporized gas molecules into highly reactive species. So these highly species, they are the ones which penetrates into the structures of these microorganisms and be able to eliminate them because they destroy their DNA. We also have a sterilization chamber, an enclosed space for where we place our items. We also have a vacuum pump that removes air prior to sterilization process. We also have a catalytic converter that after the process, we convert the hydrogen peroxide back into water and oxygen for safe handling. We have a control panel that is used to monitor parameters by sensors such as the temperature and time. And we have an exhaust system which expels the remaining gases from the chamber. So finally, let us look at the benefits and drawbacks of chemical sterilization equipment. Under the benefits, sterilizing heat sensitive materials like plastics. So we are able to sterilize heat sensitive materials. And secondly, it is highly effective at eliminating a wide range of pathogens, including those that are heat resistant. Under its drawbacks, these chemicals are toxic and potentially harmful to humans and environment. Therefore, they need handling them safely. The other drawback is that it can require longer exposure times. So it mostly, on average, it may need 1 to 2 hours. And after that, they also need to wait for the time so that we take out these gases before we can take out our objects that we have just sterilized. So at this point, this is the end of my part. Let me hand over to our host. Thank you.
All right. Thank you very much, Sam, for that wonderful presentation. I hope our audience enjoyed that part of the presentation. So let me just take this moment to remind all our audience that towards the end of last year, the Oxygen Alliance launched the BME Kwanza app. So this app is designed specifically for biomedical engineers as well as biomedical technicians. So it is a resource hub providing access to maintenance manuals and instructional videos for various medical equipment. So additionally on the app, you can actually ask technical questions and your fellow expert engineers, including engineers from the Oxygen Alliance, can contribute by sharing their knowledge and solutions. So to get the app, you can just scan the QR code that you are seeing on the screen right now, or just go on Google Play and search BME Kwanza. And just to mention, your feedback on the app is very necessary towards improving its performance as well as meeting your expectations. So your feedback is welcome, and all your feedback can be sent to us via our email, which is helpdesk@oxygenalliance.org. Thank you for paying attention. And now I will hand it over to our second presenter for the day, who is none other than Cretia Sambo. Over to you, Cretia.
Thank you very much, Victor. So for this second part of the presentation, we'll go a little deeper into the sterilization processes. So we'll look at the sterilization cycle. We'll start with heat sterilization. So it happens in 3 phases. The whole cycle is completed in 3 phases. So the first one is preconditioning. After preconditioning, we go to the exposure phase, and then we go to the drying phase. So preconditioning, as the name states, you're just conditioning your sterilization process. You're setting the conditions right so that your sterilization process is a success. So in preconditioning, when it comes to the heat sterilization, you remove air, as my colleague mentioned earlier, and then you also set the humidity right in the chamber. So after these are set right, these conditions are set right, you now go into the exposure phase. So in the exposure phase, you start to raise the temperature. So for autoclaves, for example, the recommended temperature is around 121 degrees Celsius. Therefore, the temperature starts to be raised to this temperature when it comes to the exposure phase. And then it stops per program because it has like an automated systems. You program your temperature. So after the desired temperature that you programmed is reached, the rising stops. And then for a period of time, the items or the products that you're sterilizing are exposed to this temperature in the chamber. After the sterilization process is complete, you now go to drying, where you dry your items. If they're like solids, right? So you dry them. If your sterilization products were liquids, that means they're just cooled. So basically, this is the phase. You precondition, set the temperature right and the humidity right, and then you expose it to the required temperature, and then you dry your process. You dry your items rather. So this is like a really small cycle. And then we'll just look at the pictorial view of the cycle. As mentioned earlier, we'll look at, for this explanation, we'll just look at the steam sterilization. So you are after, from the boiler steam, from the steam boiler rather, you now let your steam enter the chamber itself. So after the recommended time of your sterilization, depending on your temperature, the sterilization process will take 15 to 60 minutes depending on the temperature. So after you let the steam in the chamber and then the sterilization process is complete, and then you now dry or you now cool down your items. So this is just a pictorial view explaining the phases or to visualize the movement of the phases. We'll just use another picture for better view. So from the steam supply, you can follow the red arrows. That's your steam, and then the steam is laid into the chamber. And then after the sterilization process is complete, the steam is now laid out to the veins. So this is the blue arrows that are showing now the steam coming out of the sterilization chamber. Next, we'll look at the chemical sterilization. So similar to heat sterilization, we also have conditioning, because sterilization really needs one to set the conditions right before your process, because these conditions are typically what affects the effectiveness of your sterilization process. So we also have preconditioning. So in preconditioning, we also remove air, and then we make sure the humidity is also to the required standard depending on the type of sterilization of the chemical itself. So as my colleague mentioned earlier, that humidity is important because it acts as a medium for the chemicals in the sterilization process. So when these conditions are set right, we now go to the sterilization itself, which is the part now where you now let the gas or the chemical that you are using in your sterilization process to now diffuse or go into your sterilization chamber. After this, we go to the sterilization phase where now remove the chemicals outside the sterilization chamber. So it's also like a straightforward process. You precondition, set your parameters right, and then you now introduce the chemicals into your system, and then after that you remove. So using this diagram, there's a gas tank. So from the gas tank, after you set your conditions right in the phase of preconditioning, from the gas tank now, the valve from the gas tank is open, letting the gas or the chemical into the chamber. After the sterilization process is complete, the gas is now laid out of the chamber itself. So some of the things are just, as mentioned by my colleague, are just sensors that help you monitor your sterilization process, ensuring that you're having an effective sterilization process. We'll go deeper into the monitoring system in a few minutes. And then we have the radiation sterilization. So this one, you're basically just exposing your items or your products that need to be sterilized to the radiation, any type of radiation that you have, right? Firstly, you need to prepare your items. Ensure that they are packaged right. So other people use, depending on your facility or your setup, you can use containers, you can use pallets to package your items that will be sterilized. After this, you now expose them to the radiation. So you can use gamma radiation, X-ray radiation, and even radiation, as explained by my colleague earlier as well. So after you expose now, after your sterilization, or you have exposed your items or products that need to be sterilized to the radiation, you now have to know how to handle these products because they were recently or they were just exposed to radiation. So in post handling, what happens is that since you're exposed to radiation, that means the source of your radiation was exposed, right? So you now have to, the source of radiation goes back into its position, into its shielding, so that it does not negatively affect the people surrounding the facility or the people operating the host system. So this is just a pictorial view where you have a place where, as I said, that depending on your facility, other people load their items to be sterilized in pallets, others in containers, right? So you have a loading station where you load the items to be sterilized in pallets. And then, as mentioned earlier, they move on the conveyor belt. So when they move on the conveyor belt, which leads them to the section where they're exposed now to the treatment area, rather, where they're exposed to the radiation. So this is like the exposure phase. When they're exposed to the radiation, they, depending on the type of radiation, so for gamma radiation, the exposure of the radiation comes from more angles, multiple directions. So you're exposing your whole palette or all your items at once for the gamma radiation. But then for X-ray and the E-beam, it depends on, it's one direction. So it just radiates like one side per time. That means after that phase is complete, your items have to go through the conveyor belt again so that the other side is now also exposed to the radiation. After it's completely or fully exposed to radiation, or radiation is complete, to the conveyor belt, it now goes to the offloading stage. So after this, that's when the source of your radiation goes back to its position, to the shielding, so that it does not affect the people surrounding it. Now we'll look at key parameters of this sterilization. We've been mentioning temperature, we've been mentioning time, we've mentioned pressure, humidity, all sorts of stuff. And then what are these? So these are like the parameters, the conditions that we're setting before our sterilization process. So these are the key parameters that you look at, right? So these parameters are essential because they're the ones that set your conditions right, so that you have a successful radiation process. So the first one, we'll look at parameters that affect heat sterilization. So we have time. So your time is directly dependent on the temperature that you are exposing your items to, right? If you're exposing the items to a lower temperature, that means it will take less time. It will take more time rather to sterilize. So the more temperature, the less time you take to sterilize. So this is how this affects your sterilization. So if you misplace the settings, right, that means you might not have an effective sterilization because the balance between your time and the temperature is not there, and then your temperature has not effectively killed the bacteria. And then we also look at pressure and humidity. So these also, as we said, for the autoclave, right? So you need to have the right pressure. That's why we also have a seal. So if you don't have the right pressure and humidity, it will also affect the process. You might not have an effective sterilization. So you think you sterilized your equipment, but in actual sense you haven't, because you didn't set the parameters right according to the sterilization process that you're doing. And then for chemical sterilization, we have gas concentrations or the chemical concentration itself, right? So depending on your concentration, it will also affects the time. If the concentration of the chemical is lower, that means you need more time to expose your items to the gas or the chemical so that you have an effective sterilization. And then, as you mentioned, that we need to have the right humidity in the sterilization chamber, which acts as a medium for your gas, right? So if your humidity, depending on your temperature as well, the humidity might range from 40 to 80%. So if your humidity is not set right according to the temperature in the chamber, you're not going to have a successful radiation. So it's essential to understand how these parameters work depending on the time you want or how long you want your sterilization process to take or the temperature you've set it at. So this chemical sterilization is also considered as a low temperature sterilization because it doesn't go up as high as 100 degrees. So the sterilization process here usually occurs around 60 degrees Celsius. And then for the radiation sterilization, some of the key parameters are the exposure time, dose rate, penetration depth, and product compatibility. So exposure time is the same, right? So if ideally you have to balance depending on your dose rate or the amount of dose radiation that you are exposing your items to, you have to balance. So these parameters basically are trying to balance all these parameters so that we have a successful radiation. So if your dose rate is low, that means you require a longer exposure time. And also, as mentioned, we have as we know, or mentioned by my colleague earlier, the radiation has different penetration depths, right? So depending on your product, you have to know the type of radiation that you're using, if it's going to be able to penetrate to your items. So this is also like an essential parameter so that you're able to choose the type of radiation and know that it's going to penetrate to the desired goal. And those radiation is compatible to that product because you might end up now destroying the structure of your product because depending on the type of radiation that you're using. So if you use the wrong type of radiation or if your product is not compatible to that radiation, it will affect the radiation process as a whole. It may not have an effective radiation. So for one to have a successful radiation, you need to balance all these parameters. These are just a few. There might be more parameters that you need to also look at. Now we'll look at key indicators. So what are indicators, right? So indicators are some of the essential parts of the sterilization process, which tells you whether you have had a successful radiation process or not. So you have to measure whether that process was a success or the radiation actually happened. So these indicators can either be biological or chemical indicators. So for the biological indicators, you are using microorganisms. So I remember my colleague mentioned about spores, right? That these are more resistive to radiation or heat radiation. For the biological process, you use microorganisms that are resistant to that particular radiation process. And then at the end, if you use these biological indicators and you notice that, okay, if this resistive microorganism was able to be sterilized effectively, that means my items can also be sterilized effectively. So since these are resistive microorganisms, then now what about my items, right? So you're just comparing because as I said, you're using biological properties or organisms. Well, when it comes to chemical, you use chemicals. So these chemicals typically change color depending on the type of parameter, right? So depending on on the set. So for the chemical ones, you might have multi-parameter or a chemical that actually measures that type of parameter. So for example, you want to measure your parameter, right? So that type of sterilization, that type of indicator, rather chemical indicator, rather, will affect, if the temperature are set right, that means the color will change. I hope I'm making sense in this one. So if you want to measure humidity, if you want to measure pressure, so all these change color depending on the type of parameter that you are using to see if your process was a success. So that just indicators whether you had a successful sterilization process or not. So for here, these are just examples. In the table, we just have examples: inoculated sport test strips, self-contained biological indicators, glass ampules. So for the glass ampules, so this one, it's usually, these are the test strips that are used when you're sterilizing a liquid. So that's a special thing about the glass ampules. While for the chemical ones, you have autoclave tapes, chemical integrators, or steam penetration indicators. There are more types of indicators. Different companies have different types of indicators, or manufacturers rather. So this is just an example of the indicators. So this is the self-contained biological indicators. So for this indicator, it has all the test disposed in there, and then also the medium or the culture is tested in there. You don't need to transfer your test strip to the lab for measurements. So basically, it has everything in there to show you whether your process was a success, and you reduce the false positives. Because during the transportation of these test strips to the lab, you might be contaminated by other microorganisms. So you might feel like, okay, maybe the sterilization process was not a success while it was actually contaminated during transport. So these self-contained biological indicators are recommended because everything is done everything is done in one container in this type of radiation. And then finally, we'll look at the monitoring and control systems. So as I mentioned, that this is like a crucial process. You might not know whether you might not have your conditions set right. So you need to have all the parameters set right, and then you need to monitor the whole process, right? So we have temperature and pressure gauges. So these provide like a real-time monitoring of the sterilization conditions. And then we have safety valve, as mentioned by my colleague earlier, that so this is like an escape valve where if your pressures are higher, they now escape through this valve. And then you have sensors to detect the anomalies in the sterilization process and also ensure that there's accuracy and consistency. And then we have a computerized system. So like it helps automate the whole cycle. So how does the system of the sterilization equipment know that, okay, this time I have to precondition, or this time I now have to start raising the temperature, or this time I now have to start releasing my gas, right? Or if the sterilization process is completed. So this is how it knows. So it knows this through the automated system or the computerized system. Finally, we'll just look at where these monitoring systems are placed. So for a better view, I've just used a tabletop autoclave to just show us. So we have the pressure gauge, we have power indicators, and then we have a temperature controller, a timer, a switch. All these are a control system of these sterilizing equipment. These are like common control systems that are found in the sterilization equipment. So using these, you can monitor your sterilization process in real time and know if there's any anomalies, and automate your system using these sensors or this control system as a whole. So this was my last slide, and this marks the end of the presentation today. I'll now hand it over to our host, Victor.
All right. Thank you so much, our engineers, Samuel and Pretia, for that wonderful presentation. So reaching this point, I just want to inform the audience that the link of the attendance form has been posted in the chat. So please take your time to fill out the form so that you can secure your attendance certificate. And reaching this point, the floor is now open for questions and comments. So now, if you have any question, you can post it in the chat, or you can raise your hand and I will give you an opportunity to speak out. So just a reminder, this was an introductory part to our sterilization equipment series that we will have through the first quarter of this year. So there will be detailed webinars that will follow after this. So just be on the lookout. All right, so I can see a hand. I think it's Alfred. So Alfred, I'll give you the opportunity to unmute yourself and speak.
Okay. Thank you very much. That's a very wonderful presentation from our facilitators. Very, very wonderful. Kudos to the guys who presented. I will want to find out what happens after sterilization. Sometimes you can see a massive powder in the sterilizer. I once worked on one sterilizer, which is a steam sterilizer, and after sterilization, there was full of powder in it. What could account for that? And the autoclave is malfunctioning. It's no longer working. So, what could account for that process of what could account for the malfunction of the autoclave owing to the powder that has been generated? A very, very plenty powder. It's not a few, a large quantity of powder in the autoclave chamber. I need a little clarification. Thank you.
All right. So the powder that you're noticing or observing, so this is usually the salt, right? So this depends on the amount of water, the type of water that you're using. So if you're ideally, it's advised to use distilled water. So if you're not using distilled water, hence the salt, because now you've released the steam, so you have salt that's remaining, that's causing or that's forming that powder that you're noticing. So ideally, you're supposed to use distilled water so that you don't observe these salts for this powder. Thank you. I hope that answers your question.
All right. Thank you, Petia, for that response. And just to add, more aspects of autoclave maintenance will be covered in upcoming webinars. So just be on the lookout. But thank you so much, Petia, for taking up that question. Yeah, so I can see Good Luck has raised their hand. So I'll give you the opportunity to unmute yourself and speak out.
Hello, can you hear me?
Good Luck.
Hello.
Yes.
Yes. In terms of steam sterilization, if the machine is not working or is not generating steam, what do you do? Probably if the power is there but it's not steaming, how do you correct that defect?
All right. So our engineers, there is a question. I think he's asking. So suppose you power on the autoclave, but then there's no steaming. So what would be the solution to that? Or what is the problem?
All right. Thank you. Good luck. That's a good question. Of course, as it has already been said by our host, that most of these they'll be covered into details with different webinars. But this one, I can take it. There are a lot of factors which makes us not to achieve the steam. So apart from power, we know that steam to be generated, we have the heating elements in the steam generator. So chances are high that we have 40 elements. That's why we cannot produce steam. So that may be one of the reasons. Thank you.
All right. Thank you, Sam, for that response. I hope, good luck, you have your questions. You have your question answered. So, with interest of time, thank you everyone for joining us. But if you have any further questions or general comments that you want to give to the Oxygen Alliance, you can email us at info@oxygenalliance.org. And for technical questions, you can email us at helpdesk@oxygenalliance.org. Thank you for joining us today, and don't forget to fill out the attendance form so that you secure your certificates. Bye for now.